Hello everyone, I'm Guangxu Yang. Today I'm going to introduce our paper, Gadgetless lifting beats round elimination, improve lower bounds for point cheating. This is joint work with Xinyu Mao and Jiapeng Zhang. We are from USA. First, I introduce the point cheating problem and its applications. The point cheating problem is a natural problem where many rounds of communication is useful. In this problem, Alice holds FA and Bob holds FB. They want to compute the k-steps point cheating function, where PT0 equal to 1. For odd R, PTR equal to FA PTR minus 1. And for even R, PTR equal to FB PTR minus 1. And in k-step point cheating function, they want to compute the PTK mod 2. There is a k-round simple protocols with k log communication bits. In this protocols, anything above just compute PT1, PT2, PT3 until PTK in order. This protocol has k rounds, and in each round it costs log n bits. However, for k-1 round, previous results show that any randomized k-1 rounds protocol for point cheating with that is correct with high probability requires omega n over k minus k log n bits. They use the method called round elimination, and there exists a fundamental limitation to improve this neural bond by the round elimination method. In this paper, we improve this neural bond via a completely different method called Gadgetless lifting. And our neural bond is almost tight. The point cheating has wide applications in different areas. It can be used to prove the circular neural bonds, um, streaming neural bonds of streaming algorithm, the 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 adaptivity hierarchy theory for property testing, exponential separation in the local differential privacy, and the memory bounds of continual learning, the limitations of transformer architecture. Next, we introduce the proof outline and gauge this lifting method. First, we review the lifting series. In the lifting series, it needs a low discrepancy gated function G, and they consider the function of the form f composed with G. They prove the lifting series that is the communication complexity of f composed G is an upper bound of the query complexity of f. This means that for this kind of function, the query type protocol is optimal. However, we note that not all functions can be read as f composed G in communication community. Point cheating is an example. So that means that we can't use the lifting theory directly to prove lower bounds for point cheating, and the lifting theory need the gauge size need a large gauge size Q equal to omega n. So proving lifting theory for constant gauge size is very hard, and it is a very important open problem. In this paper, we extended the idea engineering series, we propose a gadgetless engineering framework. First, we identify a simple class of protocols. Then we prove lower bounds for this simple protocols. So in evening theory, these simple protocols are query type protocols, but in our framework, the simple protocols is more general. Next, we prove a simulation theory. We prove that every protocol can be simulated by a combination of simple protocols. That is the communication capacity of protocol compute F is equal to the communication capacity of the protocols in the simple class of protocol. In the simple class of protocols. For point shading, the simple class protocols is a case when Alice and Bob only send a value of some qualities to each other. So next we we give the um, simple class of key round protocols for point shading, and we use and we prove that every protocols can be simulated by this kind of protocols. First, Alice choose a subset I of size 10 times over k uniformly and at random, and then send FAI to Bob. Then Alice and Bob run the simple k rounds protocol, but they can skip one round if the pointer falls into I. So if the skip round never happened, Alice and Bob just simply abort at the last round. If the if a strong event happens, the protocol will be k minus one round, and we can prove that with high probability the skip round event will happen. So this is a k minus one round randomized protocol for point shading with theta n over k plus k communication bits. Next, we prove that every protocol can be simulated by the combination of the simple protocols. We achieve it by a decomposition and sampling process. First, we go back to the basic definition in communication complexity, the protocol tree. A protocol tree for each inter ver vertex V is owned by either Anis or Bob, and V corresponds to a rectangle where the inputs that need to V. And V has two chairs, U0 and U1. If V is owned by Anis, XU0 cap XU1 is a partition of XV, and YU0, YU1 equal to Y. If V is owned by Bob, YU0 cap YU1 is a partition of YV, and XU0 equal to XU1 equal to X. Each naive note specific an output. Moreover, to prove, we record the Yao min-max principle. To prove lower bounds for all randomized protocol itself to prove lower bounds for all deterministic protocols under some input distribution mu. For point shading, we let mu be the uniform distribution on all inputs. So next, we only consider the deterministic protocols under the uniform distribution. The important step in our decomposition and sampling process is density restore partition. This is this is the idea from the different theory community. First, we give the definition of mean entropy. And we use the mean entropy to describe the pseudo-randomness property called gamma dense. We call the function gamma dense if for any subset of for j which is a subset of for I which is a subset of j, the mean entropy of x on coordinate I is large. So in Eugene theory, they prove Lacan theory. For any subset x, there is a partition of x into x1 to xr, and for each xi is associated with a set I, uh, uh, II with the following properties. Xi is fixed on I, and there is the alpha I such that the x that is exists some alpha I such that xi equal to alpha I for all x in xi. And for the other part outside the fixed coordinates is gamma dense. When we also upper bound the density of the x after the partition. The density is the mean entropy loss of x. Intuitively, we this density partition achieve this kind of things. We can we can decompose x into R subsets, and each subset look like this. Some for each some there is a subset of coordinates are fixed, and for other part is dense. The dense means that it's close to uniform distribution. Moreover, in the future study, we will show that the size of the fixed coordinates is upper bound by the communication complexity. So in this method, you can just remember the intuition that we do the partition to finish these same things. So for some coordinates they are fixed, and for other coordinates they are close to uniform distribution. And the upper bound of the fixed expected average fixed size is upper bound by the communication complexity. So giving a density partition, we can give the decomposition and sampling process formally. At the beginning, we have input polygon pi, and we want to output a rectangle R. And at the beginning, we see the JGB equal to 4 sets. This is the unfixed coordinates, and we don't skip any rounds. So at the initial communication node V, if anything, we assume any's own node V, and U0, U1 be the child of V. So since any speak 1 bit, the input is divided to two parts, x0 and x1. And we just sample B1 depends on the size of x1 and x0 and x1. That is because the input distribution is uniform distribution. So we update x and v. If UB is owned by Bob, so this is the term. This is the case that Bob should speak. We further partition x into two parts by fix the parity of f they are minus 1. That means that we fix the parity of the pointer. So since the new round begin, we do the actual partition to fix the parity of PTR. Then we randomly choose one rectangle by the probability. Next, we update the x. Then for X, we do the density result partition. Get X1, Xm, and X1, X2, X2, Xm, and with some correlates. And we random choose one of these subsets, depends on probability of the size. Then we update X and GA. If Bob owns the node V, we will do a similar way, back change the role of Alice and Bob. If UB is owned by Bob, J minus 1 not in JB, we finish the skip. We will skip this round. This round. So skip is equal to true. This is the intuition for the density partition. We will fix this subset and keep this GAB dense. So for this algorithm, we prove the NOP invariant. That is, if gamma is large enough, then in the running of the decomposition and sampling process, we have following NOP invariant of each iteration. First, this is simple. X and X we maintain the rectangular subset of the of the rectangle associated with node V. And this is XGA and YGB are dense, are gamma dense. This is maintained by the density result partition. And there exists some alpha A and alpha B such that XGA bar equal to alpha A, YGB bar equal to alpha B. This is also achieved by density partition. There exists some CR such that PTR FAFB equal to R for FAFGB. This is we only need to fix the parity, but rather use the density partition help to fix the PTR. So this is the way. This is why we save the k-log factor in private result. That is the way. We only fix the parity, so we only have the constant loss. If we fix the value, we will have the log loss. So we can fix by using density result partition, we can fix the parity, and the density partition will if when we fix the parity, the part will not be dense anymore. So we density partition will tell us we will after do the density partition, the PTR will be fixed. And next, we relate to the accuracy and the average size, average fixed size. The first one is that if the algorithm prove output R and the escape is false, then with the probability of R equal to the function is small. The next one is if the escape equal to true, the probability of escape equal to true is upper bound by the average fixed size. This true number is directly followed by the uh, observation from the simple class protocols. So we skip the proof here. So if we can prove the average fixed size is upper bound by communication complexity, then we have lower bound. And math, in fact, we should plus k since for any k round protocols, the communication complexity is at least k. So the last step is that we finish this goal is that we prove that average fixed size is bounded by communication. We prove it by a density increment argument. So in the running of decomposition sampling process, we define the density function for the rectangle first. We review that the density function is the mean tree loss. So in the beginning, density function is 0. And in the backtation, in each communication bits and new round increase the density function at least 1. And in the backtation, the density function decrease at least 1 minus gamma times log n time, times the backtation size plus 1. This is by direct calculation. This is the first one is we can get by the density rule partition, and we take a expectation over the PT. The different different size of the inner density rule partition, we can alpha we can prove that the expectation of delta I is alpha bounded by 1. So since the density function is always non-negative, we can get that the the average fixed size is alpha bounded by c over 1 mass gamma log n, and gamma equal to 1 minus log 1 minus n 1 over log n. So we get our result. This is use the idea that the total increment larger than total decrement. So first, we'll give a summary of our proof. We use the decomposition sampling process to simulate to prove that every protocol can be simulated by a combination of simple protocols. And this process using a density rule partition to decompose the behavior of protocol pi into a combination of simple protocols. Then we relate to accuracy and average figure size by the just simple observation from the simple protocols. And last, we use the density increment argument to prove that the average figure size is upper bound by the communication complexity. Last, we give a form intuition about the proof of density partition. This is just a simple algorithm that start from x, we every time which is take the maximal subset such that xi is not gamma dense and the evidence. So we fix the this part as the evidence and get a subset, and we continue update the xj and I and continue the process until x equal to empty set. And we can show that the xi is fixed on ii is by the definition of algorithm, and xi g set minus ii is gamma dense since by the contradiction. Then that if J is not gamma dense, we can will avoid the mean tree condition that we take the maximal I. So that's all. Thank you for listening.